the change in electrical resistance of the carbon fiber or whatever polymer you have, one can detect which kind of material you have in the system. So for example, here is a gas sensing sensor. So these are basically made up of carbon nanotubes. So you have carbon nanotubes and polystyrene composites which form the nanofiber between the two electrodes. And when you pass air over this carbon nanofiber polystyrene electrode, what you see is the resistance is almost zero. So here you have a graph between resistance, which is the y-axis, and temperature. So they are looking into what happens with the sensing with time. So when you have air in the system, you have a resistance of 0. And when you pass in THF, which is tetrahydrofuran, along with the air, you have suddenly a high resistance. And again, once you remove the THF, the resistance drops down. Again, when you have THF, the resistance goes up. So based on the various calibration, so you can basically calibrate your sensor based on different concentrations of THF and how the resistance changes with respect to concentration of THF. And you can basically talk about whether the THF is present in the air and how much THF is present in the air. One can detect based on gas sensor. So this is sort of one of the application or one example where a gas sensor can be easily developed. So you develop your carbon nanowires, connect it to two different electrodes, look into its resistance and pass air through this nanowire and perform your gas sensing experiment. We will continue with electrochemical sensors again, and electrochemical sensors basically have tremendous application. Electrochemical biosensors have tremendous application, especially in biology. Now suppose you have a biofluid having various metal ions present in it. Suppose you have zinc, copper, cadmium, lead, as well as mercury in your body fluid. Now I have 5 different ions, and I can, using electrochemical sensor, I can detect all the 5 different ions, or presence of all the 5 different ions simultaneously. Why? Because if you remember, when we were looking into electrochemical technique, I talked about the electrochemical series. What was the electrochemical series? We saw that electrochemical series depends on the depends on the various metal ions, and it had different voltages or reduction voltages. So based on the electrochemical series, by passing a particular amount of current through this system or through the sensor, I will obtain at different potentials, different ions will be reduced. And if I have again a calibration of all the different ions, then I can basically calculate or estimate what the concentration of these different ions is at different potentials. So this electrochemical sensor becomes just one sensor which can be used to immediately find out the concentration of different ions. Not only that, if you are usually, in case of sensors, you want it to be accurate, not only accurate, but you want to make sure that it is 100% certain that it is the correct value what you get, especially in case of biosensors, because the medication which you get based on your analysis is going to be dependent on the sensor itself. And if the sensor gives a wrong result, then you might have a detrimental effect during taking the medication. So in case of electrochemical sensors, you can not only reduce the metal during the process, but you can also oxidize the same metal once you have reduced it, and then reconfirm. So based on just one single experiment, you're reducing it to the metal and oxidizing the metal to its ionic state. And in one step, you're reconfirming that yes, you have all the materials present and all the concentration of the material present. So in one step, you're getting a complete proof, a sort of complete proof that you have the different metal ions. Now, electrochemical technique, as we saw before, you have 3 electrodes. You have the working, counter, and reference electrode, which we discussed. The same electrodes can be developed into the device which is over here. So again, you have here gold as working electrode, gold as counter electrode, and silver as the reference electrode. So this is a slightly different setup where you have bismuth as well as two different working electrodes to improve its sensitivity. Over this setup, you have a layer of Nafion. Nafion is used because it's a proton conductor, and in case of water-based system, ideally slightly acidic-based system, these membranes help in generating a lot of, it helps in ionic transport and therefore improves the signal of electrochemical sensor. So the final setup of the simple electrochemical sensor for detecting different metal ions in body fluid would come out like this. So in the proper production, when you have a production of sensor, your basic sensor is going to look like this, which is shown over here, and you put in your drop similar to what a diabetic, when you have sensing of glucose for a diabetic patient is. It looks something very similar to this. So it is rather simple. Once you have a possible detection way, or if you have a biosensor which you can for which you can detect different molecules or different ions in your lab, it is very simple to take it from the lab scale to a commercial scale in case of sensors. However, in case of biosensors, there are various important aspects, especially if you want to have a bacterial biosensors. There are various parameters which are a requirement from the government or from the health commissions, and these requirements are important to address when you make a biosensor. So it has to have a sensitivity of 10 to the power 3 CFU per ml. It has to have a specificity with different bacteria. So this is only for bacterial. Of course, the same thing will be useful, or same conditions will apply to other materials as well, other biosensors as well. The speed of sensing has to be between 5 and 10 minutes. You should, of course, when you are having a culture, bacterial culture, you have to wait for 3 or 4 days for the bacteria or virus to grow. But when you want to have fast detection, one has to detect, the speed of detection should be, for a sensor, especially in case of glucose sensor, the speed of detection should be within 5 to 10 minutes. The size has to, obviously, when you want a portable sensor, the size has to be small, and minimum sample preparation is needed for the sensor. And the sensor, although it is very sensitive to atmosphere, one has to look into how whether the sensor can be stabilized with different atmospheric condition and different temperature conditions, and how does the impurity affect the sensing property. So these are some of the critical aspects for understanding or developing better sensors, especially biosensors. So what are the factors which affect the sensing properties? Again, it comes down to synthesis method. Surface area plays a very big role here, because the more the surface area, the better the sensing. Functionalization of sensors is also an important aspect, especially in case of biosensors. How does the impurity affect the sensing property? That also has to be determined before. And the noise ratio. So what is your background noise for sensing? Is it microamps? So for example, for electrochemical sensor, is it nanoamps or picoamps? What is your noise ratio? Where would you really say that this is not because of the noise, and or how the impurity is going to affect your noise ratio? So these are some of the key factors in improving sensors. So with that, I come to the close of this section of solar cells and sensors. And before I end the session, we won't have a quiz. Don't worry about it. And this time, we won't have any quiz over here. What I would like to show you, which I found today morning while reading the journal paper Nature, is science for fun or for application. Always most of us are looking into science in terms of an application. We are trying to solve a problem. We always look for publication. We always look for research grants where we can get this scholarship or that scholarship. We are always running behind these research grants and papers and everything. But there are times where science can be really fun to do. For example, here, if you read yesterday's Nature article or Nature journal, Nature publishes every weekly journal, and I usually look into the Nature journal every Friday just to see whether there are fascinating things which have come out or not, or whatever latest aspects of research is coming out. So here I found in today's yesterday's issue, there was a very fascinating article whether water can be metallized or not, or can you create metal out of water. So this first example of metallized liquid, we know only liquid metal as mercury or gallium. If you take it over a certain 29 degrees Celsius, it is liquid. Now, can you make a liquid as conducting as a metal? And here the challenge was sort of, can you make water into a metal? So water is not a metal, everybody knows about it, but can we make water into metal? So these guys, they did something very clever. This was first observed by Humphrey Davy. When you have alkali metal and you expose it to ammonia, you can metallize ammonia for a certain amount of time. And electrons go from the alkali metal ion to ammonia in order to make it a metal. So the same phenomena, they tried it with water. Of course, if you want to metallize water, it has to be done at very high pressure and high temperature conditions. So therefore, it is not, especially high pressure condition, which is not feasible. So these guys did the very clever experiment. They took sodium potassium alloy, because sodium and potassium are liquid at room temperature and they can donate electrons. And what was fascinating was within a fraction of seconds, so there is basically 3 seconds, you can see that the water has become golden in color, and that is basically metallized water. So this is just for fun. Will it have any application? No, it might not have any application, but this is science for fun. And there is a video basically showing the whole process. If you go through the Nature paper, it's a 11 minutes video, but I'll just pull it to the most important aspect of the video, which is at the end, I guess. Yeah. So here they have made a home-built experimental setup. That's another important aspect. Whenever you're doing science or whenever you're trying to build something completely new, think of how one has to develop the instrument, what kind of experimental setup you need to develop rather than just buying it from the shelf. So these are different ways to do very clever science. So they develop their own equipment, they develop their own instrument in order to use this for making metallized water. So this is what they are seeing. You can watch the video online. The link is given over there. So what they have done is they've taken a syringe and they have they're making a alloy of, they're passing the sodium potassium metal on, they're passing the metal through this syringe and then dropping water on the top of it. And what you see clearly is that water becomes golden in color and the spectrum on the right side goes on increasing. So this is basically a beautiful way to show that science is not always for application, but also you can have fun with science. So basically what we have learned in this class, we have basically looked into the device application based on nanomaterial synthesis. We looked into two systems, the solar cells and sensors. We talked about solar cells. We looked into various types of solar cells and discussed a bit about dye-sensitized solar cell and the latest perovskite-based solar cells. In sensors, we looked into various sensors and what are the important factors which basically affect the sensors, or which one has to take care to develop sensors. So with that, I come to the close of this topic. And if you have any questions, you can contact me, or you can basically we can have a discussion now. Thank you very much.
Thank you, Professor, for excellent and fun of science. So really, your talk is very inspiring one.
Thank you, thank you.
And this is also special lecture, I think, because of the last day you have taken us very good informative lectures. All the lectures are very good and excellent and informative.
Thank you.
Yes, Professor. This is a time for asking any doubts or clarification. Please, you can unmute and then interact, friends.
Abhishek, congratulations. Your lecture is very fascinating and a very interesting one.
Thank you, Professor. Thank you.
And lastly, you have displayed some work appeared on nature, so it's really a very interesting. So,
yeah, I always I always, because I don't want this. I mean, the audience here, I guess many of you are research scholars and PhD and master's students. What I would sort of like to say that don't take everything every time seriously. That publication is a rat race. Okay, it depends completely on lot of factors, the number of contacts and everything. But science is always for fun. You're doing science for fun as well, and look into the fun aspect as well. Not always as from a scientific purpose. Like we are. Of course, it is important that we have to make to develop devices and things, but there are fun aspects as well, which one usually forgets when doing science.
Okay, thank you.
Good afternoon, sir. Preeti, a research scholar from MNIT Jaipur. Actually, sir, I wanted to ask you, how can we quantify the concentration of analyte present in the air or the environment?
That's a tough question, I would say. As far as ideally, when you have analytes in air as such, when you're making a sensor for air, it's quite difficult. But when you want to quantify it in a lab, it is easier. When you quantify it in a lab, you usually use gas chromatography in order to identify the various concentrations. So that is the simple answer. But when you want to do it for air as such, then it becomes a really difficult aspect. In case of lab, I can say that it is easy. So you can pump air through the gas chromatography in order to find out what the different concentration is. But as such, because air is in just an environment, it becomes such a volatile aspect. From morning to evening, there will be a huge shift in the concentration of various things. So that becomes an issue.
Okay. Thank you so much. Thank you.
Yep.
Hello.
Hello. Yeah.
Yeah. Good afternoon, sir. Myself, Dr. Pragati Kumar from Central University of Jammu.
Yep.
Sir, will you tell me what is the exact meaning of sanitized this solar cell? Sensitized solar cell.
Dye-sensitized solar cell, you mean?
Yeah, sensitized means what means sensitized particular meaning, because I have searched a lot of, but I have a lot of confusion regarding the exact meaning of whether it is quantum dot sensitized solar cell or dye sensitized.
Yeah. So basically, what is, I mean, when you say dye sensitized, because the dye is a sensor for taking up the energy, or it can take in the energy from the sun. So therefore, that is a sensor, acts as like a sensor.
Means nothing is related to its construction, means like whether it is decorated, means in terms of the quantum dot. If I am talking about the quantum dots, then nothing related to whether it is decorated or embedded or composite.
So but these are sensitized basically means you're sensing something. So dye sensitized or quantum dot sensitized is it's taking up the energy, so therefore it is acting like a sensor. So that's the reason it's written dye sensitized solar cell, because the dye is the sensor which is absorbing the energy.
Means whatever be the absorber component.
Exactly.
It is independent on the means it's you can say a microstructure or construction.
Exactly.
Yeah. Okay. Actually, that was my confusion.
It is a general term. It's a general term. Nothing.
Okay.
Yeah.
Thank you.
Yeah.
Okay, thank you, Professor. Participants, if you have any other queries. Yeah. So, hello, sir. Can you hear me?
Yeah,
Yes, sir. I think there is no other questions. Shall
good.
we conclude this session?
Yeah, definitely.
Yeah. So, thank you, Professor, for the end of this lectures today. So, on behalf of Alagappa University, India, and Brunel University, UK, so on behalf of organizing committee, I would like to thank Professor Abhishek Lahari for giving a wonderful lectures on the application of solar cells and sensors. So he has detailed explained the thing of how the solar cells and the sensor will work in this area of nanomaterials, and how this important role of science as making a fun through this sensors and solar cells. So really, I thank you so much, sir, for giving a tireless and continuous support for the lecture.
Thank you very much.
Really, this conference was successful because of the UK team like you and Kumravel, Professor Mani, and Professor
Thank
G.
you.
Ravi sir, etc. So, really thank you, sir, for giving a wonderful lecture.
But you are the most important person because you are the one who organized it. So thank you.
Thank you so much, sir. I think further delay, shall we go on for the validity function?
Yeah.
So please join, and maybe another 2 minutes we'll start the session of validity function. So let me check, Professor Jayal sir. Good evening, sir. Good evening, sir.
Good afternoon. Good
Yeah,
afternoon.
good afternoon, good evening, sir. Professor
Professor
Sekhar sir. Professor Visitor sir.
Satyavel, how are you? We are being only online.
Fine, sir. Fine.
Good to see you.
Hello. Welcome, Jay. Welcome, Dr.
Good
Jay.
evening, Ravi. Good
Good
evening.
evening. Good evening. So, on behalf of the Spark, I welcome our registrar, Professor Sagar, Professor Jayvel, Dr. Saktivel.
Team Biscuit is also virtual.
Sir, I think we are waiting for another development actually. Sir, just a few minutes, sir. We are waiting for Professor Brunel, sir.
Okay, fine. The man.
The pink one. Pink one to be ready.
Professor Segar sir, Mr. sir, can you hear me, sir? Sir, can you hear me, sir? Sir, can you hear me, sir? That mic is
Yeah.
not working actually.
His audio is muted, but he is responding. He is looking
Yes,
at
sir.
the.
Yes, sir. Sir, here in this forum, Professor Abhishek Lahari from Brunel University. So you just please interact with us for 2 minutes, sir. So meantime, HOD sir will connect in the line.
Okay.